scared.
You got this, girl.
1. No, now I have to go down.
Oh boy, but you're joining me at least. All right. Okay. Oh my God, that's a 2.
Oh my God.
What?
I'm at the pet show, and I'm a winner. What did I tell you at the beginning of the game?
This is crazy. How did you do that?
Well, I happen to know a little bit about Markov Chains, which I researched after learning all about linear algebra in our class with Dr. Peichnik. Do you guys want to hear about it?
Yeah,
Sure.
I think I missed that.
All right.
Is that how you won?
Yeah.
Whoa.
So a Markov chain, much like our Chutes and Ladders game, is a system in which the next state of affairs depends only on the current state of affairs, which is to say it's a process with no memory. It doesn't matter what your move was 2 moves ago, it doesn't matter about the last time you played. It's only about the last state. And we can use tools from linear algebra that we've been learning from Dr. Peichnik to analyze systems like this and create predictions for long-term behaviors of the system. So the first thing we need to define is the situation we're trying to address. And in mathematical terms, we're going to call that the state space. And it's represented by a set. It's going to look something like this. A state, something like a set of properties. And it can be as long as you want. And each of these is just a set of possibilities for each of these properties. Let's talk about an example. In this example, we're going to talk about whether or not I see a squirrel named Penelope outside my window based on whether I saw her or not today. So this is our general form of state space. Our state space for our example is just the possibility of seeing Penelope or not seeing Penelope. And this situation, in this general situation, there will be a state vector which describes our current state of affairs. So our first state of affairs, let's say today, I saw Penelope. Now these numbers in here are probabilities. They will always add up to 1. And right now we're going to start with a probabilistic unity where I know that I saw Penelope today. And we're going to work through a process and see what the long-term likelihood of seeing Penelope is. Now, the next thing we need to define is a transition matrix. Now, a transition matrix is going to do the bulk of the work. The transition matrix is an n by n matrix where n is the same number of properties or elements you have in your state space. So for now, can anybody tell me what our matrix is going to look like?
2.
Yes, a 2 by 2. Perfect. So we're going to just make up some probabilities here. The topic of how we get to these probabilities we'll address later. It can be done by experimentation, it can be deduced sometimes, but for right now we're just going to put in some dummy numbers that are easy to calculate with so we can see what's going on. Now before we do that, we make our matrix, we're going to need to use a table to try and understand what we're looking at in our matrix. So how we read this table is these over here are the current state of affairs. And the numbers I fill in here are going to correspond to the likelihood of these happening given our current state of affairs. So if you bear with me, I'll give you an example of what that is. So in this instance, I saw Penelope today. That means I have a 0.7 or 70% chance of seeing Penelope tomorrow and a 30% chance of not seeing her tomorrow. So this is going to directly translate into our transition matrix, which is going to look just like that table, and it reads just like that table, but it's in matrix form, so we are allowed to do all of the operations that we learned about the matrices can do. So when you see one of these transition matrices, you can read it just like this. Now, a few other things we need to define are, one, the time step. So you notice we're talking about evolution over time here. Now, an important thing is that this is not a continuous evolution, this is discrete. We have a discrete time step. It's called between each state, and each state is a relevant time about the system that we're trying to predict. So we have the relevant situation where I've seen Penelope today, and then we have a time step of 1 day where we're looking at and trying to predict whether I see her in the future. And in the long term, if you carry this out over as far as it can go, you will reach something called a stationary distribution, which is a property of the Markov chain. And it is generally what people are looking for, is an accurate stationary distribution. And that is just another state vector that gives you the probabilities in the long term of anything occurring. So it may not be tell me about exactly what's going to happen tomorrow based on today, but it will give me an average probability in the long term that will help me to predict whether I see Penelope tomorrow. All right, so let's evolve these things through a few states, just like we might, like I did for the board game, so that I knew what was going to happen. So let's take our state vector and evolve it through time using the transition matrix. Now, how this works is through basic matrix multiplication, like we've learned how to do in class. It's a little tedious, so I've already done the calculations. I just want you to see what the process looks like and how these numbers are interacting with each other. So right here, I apologize, should have been S of t. So that is S of t is going to represent our initial state. Where I saw Penelope today, I'm wondering if I'm going to see her tomorrow. And the way we do that is we're going to come over here and we're going to look for S t plus 1, which is going to represent our time step of 1 day into tomorrow. And the way we do that is we place our row vector on the left of our transition matrix, and then we just perform regular matrix multiplication. Like I said, I saved us the work, so I'm just going to show you what this turns out to be. And it's fairly obvious, if you look at it, that it's going to turn out to be 0.7, 0.3. And that's going to be S of t plus 1. Now the same process you can carry out as many times as you like. And eventually we will reach a stationary distribution. We see how one time evolution has gone through this, right? So if we keep going, you're going to have to trust my calculations, which is generally not a wise decision. It would look like this. And let me just show you the formal way to write this so you kind of see the nuts and bolts of what's going on. So now we're getting S of t plus 1 times, let's call our transition matrix T, which is going to be equal to this. I'm just going to write T here to save time. That means this transition matrix, that stays static in these. It's just one set of probabilities for all of them. So we evolve this through. It's going to look something like, and notice that these are all always adding up to that probabilistic unity 1. Let's do just one more. I'll show you what the value of that is, and you'll see why that's important in a moment. St plus 3, which is the third day, is going to be something like 0.58 and 0.42. Did a little bit of rounding there just to keep it simple. Now, as I said, we go long enough with this, we're going to converge to what is called the long-term distribution. Unfortunately, we can get there through a much quicker method. I just wanted to leave this here to show you that the results will be the same. Okay, so now that we've seen how this time evolution works, I'm going to show you a shortcut as to how you can do this without all this annoying matrix multiplication, or at least a little bit less of it. And it's this sweet little trick where we're going to find S of t star, and I'm just putting this to represent any evolution, any distance in the future we want can be reached. The result will be the same as this, and it can be reached by this process by just taking our initial state vector here, which we named S of t, and multiplying it by our transition matrix raised to this t star power, where t star is just whatever day we want. It can be 10 days, it can be 30 days, it doesn't matter. And if you do this process where this power just really means taking these two matrices and multiplying it, this one matrix, and multiplying it by itself, just like that, and it would act like you would think. You just have the matrix side by side, and you just do it one at a time, and if it's cubed, you do the next one, and so on and so forth. And you will end up with the same exact value you found for those with a little bit less effort. And now that leads us into what our ultimate goal is a lot of the time with Markov chains, which is a long-term steady distribution, which is actually what you'll get if you use that equation I just showed you, or if you do this enough times, you will reach, a state where the numbers no longer change. Now, in order to tell you what that means mathematically, I'm going to need to talk about eigenvectors really quickly. Okay, so we fortunately just talked about eigenvectors in class, but as we can recall from there, an eigenvector is simply a vector that when multiplied with a matrix is that same vector times a scalar. So the equation that we are familiar with is, say, T, our transition matrix, times any old vector is going to equal lambda times that vector, where lambda is a scalar. And that is an eigenvector of T, which is a very important thing. An eigenvector is always an eigenvector in relation to the matrix. It's not just a thing, it has to be in relation to the matrix that produced it. Now, what's different in Markov chains, if you haven't noticed, is that we're using a row vector. The ones we learned, the vector is on the right, and it's a column vector. So what we're using Markov chains here, as you see, our setup is actually called the left eigenvector because we have to use our row vector on the left. But it abides by the same rule. It's just if you multiply it through that transition matrix, it's just the same vector multiplied by a number. So how does this relate to our overall goal? Well, the steady state distribution of a Markov chain is defined as, and this is very strange, the first time I've ever seen pi used as a variable and not as our nice little circular friend, is pi times our transition matrix is equal to pi. So pi is a state vector representing our steady state distribution, our long-term distribution. And what this definition says is that if we feed this vector in through that matrix, all we get is an eigenvector with an eigenvalue of 1. And that is the definition of our long-term steady state distribution.
Wow. How does this relate to chutes and ladders?
Well, let's illustrate this with an example.
Oh, that sounds good.
Yeah, because there's no other better way to learn than with an example, right?
Yeah, excited.
Right, so let's say we have like a mini chutes and ladders game, right? Just to make things a little less complicated and have not 100 squares. Let's say we had 4 squares in our new mini chutes and ladders game, right? In which we have states 0, 1, 2, 3. And let's say we flip a fair coin, right? Because we don't have a spinner in this little mini one because, well, 6 choices in a spinner, the game would not work that way. Right, so this is gonna be a little too hectic. It could work, but just a lot of calculation. So, and this is in our oversimplified example, so we'll go for this. So, let's say we flip this coin, right? And we can get a heads or tails. Right, and when we have a heads, we move forward 1 square, and then if we have a tails, we move forward 2 squares. If a move would go beyond a 3, you would stay where you are, essentially meaning that, like, just like in chutes and ladders, where it's like, let's say you're at 99 and you hit it and you get like a 6, you're just gonna stay at 99, right? Yeah, and then also if there's a chute, so if you land on square 2, you would slide immediately back to square 1, right? So in this situation, we're going to model this as a Markov chain and find the expected number of turns to reach the finish, starting from 0.
Seems like there's like a lot of different like transitions in here.
Yeah, so we're actually working with state transitions.
Oh, that's one aspect of Markov chain, right?
Yeah, that's what you were actually reminding me of. There you go.
Wow, you guys are so smart. Wow, that's great. Amazing class here. Anyway, so let's say we had E of I, right? And this would represent the expected number of turns to reach square 3 starting from square I, right? So I could just represent like any of these squares, right? So, and our goal is to make it here, of course. All right, so finish line. So we already know that E of 3 equals 0, because if we start from 3, we're gonna be done, right? So, like, if we start from square 3, we're done, right? This is our starting.
Yeah, we don't have to move anymore. There's nowhere else to move.
Right, you already finished, you're good. You're good. I'm so proud of you if you did that. Yeah. So if you land on 2, right, you slide immediately to 1, right? That's our chute. Womp womp, right? So E of 2 would equal E of 1. Right. And so let's say we start from 1, right? So in this case, this is just I equals 1. Right. If there's a heads, right, that means you just go up 1 square, right? So you start from 1, you go up 1 square. Where's that gonna send us, guys?
One square.
You send us to 2.
Yeah, it sends us to 2. But we're
It
just
sends you back.
sends you back.
Oh my god.
Oh no.
Oh no.
No.
Oh no,
That's terrible.
Yeah, so how do we go from here?
Guys. Let's think about
I think
it.
we can work through this.
We can work through
Let's
this.
think.
We can work through this.
Let's think. What
So-
would Markov do?
Yeah.
What would Markov do?
That's a good question. What would he do?
Right. So if there's a heads, right, and you go to 2, right, that's just gonna slide you back to 1, right? Essentially representing the E of 2 equals 1, right? And then if you have a tails, right, so we're starting from I equals 1, we go up 2 squares, that sends us to 3, we're done, right? So tails would just mean you go to 3, and then you're done. You're finished.
Wow.
Great. So if we want to represent E of 1, right, then we would we would get the number of turns. So we'd get 1, and then plus half of E of 1 plus half of E3. Right.
And why do we have them again?
We're halving them because we're trying to like find like the average of it. Like we're flipping a coin, so there's gonna be a half probability. Right.
That makes
That explains
a
that
lot
one
of
half.
sense, actually.
Yeah. So basically from there we know that E of 3 equals 0, right? And then that would mean that we get half of E of 1 to equal 1, so that means E of 1 would equal 2. Right? Now let's say we start from 0. Right? And so if we have a heads, right, then a heads right here would send us to 1, but if we have a tails, it would send us to 2, which would send us back to 1, right? So E of 0 would equal 1 plus 1 plus 1/2 E of 1 plus 1/2 E of 2, right? But E of 2 equals E of 1, right? Right, so that's just going to get you 1 plus E of 1, right? And so that's just going to get you, which we've already set up,
Oh, 1 plus
2.
2.
which equals 3, right? So E of 0 would equal 3, meaning that it's going to take 3 turns on average to reach the finish from the starting square.
Wow.
Wow.
That was so informational.
Thank you. Thank you so much.
Thank you so much.
Of course, I'm always here to help.
All right. So after we learned about board games, let's talk a little about something more fun, like population migration. So Markov Chains are really useful when it comes to determining where somebody's going to be at. For example, if we can use it in rural applications, climate change is a big topic. So we can, for example, we're going to have climate refugees. We can determine population migration of climate refugees. We can even determine something as simple as like how many people left from New York City or were going to leave from New York City during COVID. And this is the functionality and the application of Markov Chains. On that note, let's start off with a simple question. So imagine a world, the regular New York experience, where there's only 2 places that matter. So at present, 85% of the total population lives in New York City, and 15% lives in New Jersey. So they're suffering. But each year, 10% of the city, people in New York City, move out of the suburbs. New Jersey, which I believe is suburbs. Wow, only 5% of New Jerseyans move to NYC. Assuming that the total population remains constant, what percent of the total population will remain in NYC after 2 years? So we're going to determine this massive move of about 10% of the population moving out in NYC after 2 years of this great migration, for either a climate crisis or just for cheaper rent. So let's create a nice little diagram. That adds up to 1, because that is important and necessary. So here's NYC, here's probability, here's 0.9, here's 90%, and here's the 10% going, that we are determining the probability chance of them going to New Jersey. And let's write it for New Jersey, give me a sec here. 0.95, and here is the 0.05 going to NYC from New Jersey. All right, as determined, and as we have specified before, let's look at the initial probability distribution. So, VO NYC, New Jersey. And as always, when it comes to Markov Chains, we need a transition matrix. So P equals NYC, New Jersey, Zero 0.9. All right, and this is what we want to determine the total, how the total population will remain in NYC after 2 years. So this is the formula we will use to determine, to pretty much evolve the transformation matrix.
Hey, those matrices look a little bit different than the ones Jasper used. Why is that?
Oh, well, that's because I'm using columns instead of rows. I don't believe it matters which one you use. But if you enjoy columns more than you enjoy rows, go with columns.
Would you say you're a columnist?
I would say I'm much more columnist than a rowist. Anyway, going back to the problem. Thank you, class. So we do a matrix multiplication, and we square the transition matrix because we have to look 2 years out. If you don't remember, class, this pretty much becomes this, so we can envision the matrix multiplication. This will be on your test, the final, from PJ. And just imagine a perfect world where we solve everything perfectly. We can just imagine everything being solved, and we end up with this matrix right here. So this is the final matrix, the evolved matrix. All right. Sorry, let me break that better. All right. And because luckily we're not looking out, for example, over long term, we're not looking to a distant future that we can't determine. We're not really looking for like a more static state. We can pretty much just take this. So we take the percentage of from NYC, the percentage from New Jersey, and then we add it by the initial probability distribution. We multiply by the initial probability distribution, and then we add it. And then we're gonna determine the total amount of population from this simple calculation that will remain in New York City after 2 years. So, got lost it.
85.
So at after 2 years, only 70%, 70.7% actually, of the population will remain in New York City, and the rest of them are enjoying cheap rent in New Jersey. And yeah, that is how you can use a Markov chain to determine population migration over a course of 2 years. You can increase it to 3 years, 4 years, 5 years. And yeah, this is why Markov chains are very nifty, and this is really good intuitive tools to predict outcomes of the future.
Another application of these Markov chains is in PageRank, and that's when anytime you use a search engine, they're going to rank the pages based on what's the most important. And one early model that search engines used was the random surfer model. So for this to work, we assume that our random internet surfer, he is going to move randomly between websites that are linked to each other. So within websites, you could click on links, they'll take you to other websites. And how we want to do this is, let's say we have websites, so A, B, C, and D. So he's going to randomly go between these websites, and to determine the importance of each of these websites, we want not only the website that has the most links to it, but the most important website will also have links from other important websites. So that's why Markov chains come in. And so let's say our website A links to D, C, and B, and that website B is going to link to C, website C is also going to link only to A, and then D also links back to A. let's say D and B also link to each other. Okay, so let's say these are links. So our random surfer will start on any of these websites. So let's say if he starts on A, he will randomly click on any of the links. So there's a 1/3 chance he ends up on any of the links. And if he goes to B, if he started at B, there's a 1/2 chance he ends up at either D or C. And then C only goes back to A, so that's going to be 1. And then same with D to B, only links there, so it's going to be a 1. And our surfer will never go back to the same website, so if he's on A, he will not go back to A. So to put this in a matrix, we're going to have, so this is going to be from A, B, C, or D, and then they're going to go to either A, B, C, or D. So the probability that he goes from A to A is 0. The probability that he'll go from A to B is 1/3 on here. And that's the same for C and D. And then to go from B to A, there's no link there, so that's going to be a 0. B to B is 0, and then there's a 1/2 chance for C and D. C only links to A, so that's going to be 1 and then 0 down. And then D only links to B, so that'll be 1 there and 0 down. And so then something special about this matrix is that it is a column stochastic matrix. And this means that we have a real square matrix, all the elements are positive, and then each of our columns you'll see sums to 1. So because we have a column stochastic matrix, when we go to look for the eigenvalue, so if we want to determine the steady state, earlier was mentioned that this V here is going to be your steady state. So when we do A minus I, your vector, like we were talking about finding eigenvectors, instead of having to go through and find all the individual eigenvectors, we can use the, sorry for my pronunciation, but the Apparin-Frobenius theorem. Which says that there will be a unique leading eigenvalue for these stochastic matrices so that the corresponding eigenvector will be all positive. And specifically for a column stochastic matrix like this, the highest eigenvalue you can get is going to be an eigenvalue of 1. So that's going to make our math really easy when we go to solve for this. So, fix this. So we're going to want to take our matrix and subtract, here, let me bring this back. Okay, so we're going to have, since this is 1, you're just going to have your normal identity matrix. Which will lead us to having 1, 0, 1, 0, 1/3, 0, 0, 1, or negative 1, 1/3, negative 1, 0, 1/3, 1/2, 0, negative 1. And so we're going to then set this matrix equal to the 0 vector. And so we're going to want to row reduce it. And after you row reduce it, you're going to have the matrix 1, 0, negative 1, 0, 0, 1, -4 over 3, 0, 0, 0, 1, -1, and then all zeros down here. Oh.
You're good. Keep going.
Alright. And so then we'll have our equation so that we can solve for the vector. So because you have a row of zeros, v4 is going to be a free variable, so we're going to set that to 1. And so then v3 minus v4 is equal to 0, so v3 is going to be 1 as well. We're going to have v2 minus 4 over 3v3. So our v2 is going to be 4 over 3. And then v1 minus v3 equals 0. So v1 is also 0. I mean, also 1. So we're going to have, here, let me erase this. So then v is going to equal 1, 4 over 3, 1, 1. And to get this to be probabilities, we're going to add up all the values in here, which is will get us to 13 over 3. And then we're going to divide the matrix by this value. So we're going to have 3 over 13 times 1, 4 over 3, 1, 1. Which will lead us to having the probabilities of 3 over 13, 3 over 13, 4 over 13, 3 over 13, 13. And as you see, this will also sum to 1. So then there's when our random surfer then is moving around these websites, 4/13 of the time he will spend on website B, and then 3/13 of the time he'll spend on everything else. So B becomes our most important website because he'll spend the most time there if you're randomly going between websites. So that's how you find the steady state vector for your transition matrix.
We have a simple train system with 3 stations that are equally spaced called A, B, and C, each with identical traffic and other conditions. Let's let each state of our process represent the corresponding station, and let each state have 3 possible delays: early, on time, and late. Suppose a train at station A has a 10% chance of being early, a 60% chance of being on time, and a 30% chance of being late. Then we can represent our state vector at A as 0.1, which is the probability of being early, 0.6, the probability of being on time, 0.3, the probability of being late. Let's then introduce our transition matrix. T equals 0.7, 0.2, 0.1, 0.2, 0.5, 0.3, 0.1, 0.3, 0.6, where, for example, this entry represents the probability of being early at station A and still early at station B, and this being the probability of being early at station A and being now on time at station B. We can then write our Markov transitions as follows. S sub B is equal to S sub A times the transition matrix T, and S sub C is equal to S sub B times T, which, if we plug this in, is equal to S sub A times T squared. Now, doing out our matrix multiplication, we can obtain that S sub B is equal to 0.22, 0.41, 0.37, and that S sub C is equal to 0.273, 0.360, 0.367. Corresponding to probabilities of being early, on time, and late at each of these stations. Now, if we have more stations, we could, of course, do more steps of this process, and we could also find the long-term limit if we had infinite stations by taking the same thing with eigenvalues and like long-term prediction. But what we have so far is called a first-order homogeneous Markov chain. First order represents the memory of the system. That is, the probabilities at C are only dependent on the probabilities at B. But we can also have, like, for example, second order, where the probabilities at C are dependent both on the probabilities at B and the probabilities at A. For example, through this transition and this transition, which we've done before, and also through this transition, which is new. Meanwhile, homogeneous means that the transition matrices between each state are equal. For example, the transition matrix between A and B is the same as the transition matrix between B and C. What we've examined so far is what's called a first-order homogeneous Markov chain. That first order represents the memory of the system. That is, the probabilities at C are only dependent on the probabilities at B in the state before it. However, we can have higher order Markov chains. For example, for a second order Markov chain, the probabilities are dependent both on B, the probabilities at B, and the probabilities at A through this transition and this transition, the same ones that we mentioned before, but also through this transition, which is new. Meanwhile, homogeneous means that this transition matrix is fixed between any two states. For example, the transition matrix from A to B is the same as the transition matrix between B and C. While first order Markov chains can be good to model these types of train systems, the assumption of the Markov chain being homogeneous, however, does not. For this, let's consider the one train at 34th Street Penn Station, 42nd Street Times Square, and 50th Street. Because the probabilities at delays stemming from each station are not the same for a variety of factors. For example, different amounts of traffic means that more people hold open the doors, or more people have to get on and off at the stations, causing greater potential delays. Furthermore, the distances between the stations and the distances between the stations may not be equal, and the trains may have to hold between some stations, also increasing the likelihood of delays at certain stations, but not others. As a result, let's introduce a non-homogeneous Markov chain. Let's let each state be a new variable s, where, for example, this is x equals 1, this is s equals 2, and this is s equals 3. Let's define the state vector at each state, as before, as a probability of being early at s, the probability of being on time at s, and the probability of being late at s. Let's now introduce a new transition matrix, T sub s, where s denotes the station that it originates from, because as mentioned before, this can no longer be constant. This would be equal to a probability of being early at station s and early at station s plus 1 of s, the probability of being early at station s and being on time at station s plus 1, at s, etc., and the same relationship for the going down. The probability of being on time at station s, and being early at station s plus 1, etc. Let's now make this even more general. That is, instead of just being early, on time, and late to characterize our delays, we instead have the delays be represented by negative n to n, where n represents the train being n minutes early, and n representing the train being n minutes late. Now, our state vector at s is equal to the probability of being n minutes early at s, the probability of being n minus 1 minutes early at S, etc., all the way up to probability of being n minutes late at S. Our transition matrix now is defined similarly to as above, just with n's instead of e's, o's, and l's. For example, here it would be probability of from negative n to negative n of S, probability of from negative n to negative n plus 1 at S, etc., all the way up to probability of being n minutes early at station S and being still n minutes late at station S and still n minutes early at station S plus 1. So now that we've established how you can use Markov chains to relate the delays between stations, let's find how you've determined the numbers, how you actually determine these probabilities. Well, that is by analyzing historical data. Let's take the 2 train between 96th and 72nd Street, for example. Let's try Let's try finding the probability of the train being 3 minutes early here and just 1 minute early here. Then you find the number of instances where it's 3 minutes early here and 1 minute early here, and divide by the total number of trips to get probability from -3 to -1 of S, where S is whatever you define this as. Even if you don't have the historical data needed to back this up, for example, if there are no trips between these two stations with a specific combination of delays, then you can still infer this using complicated stuff. So Jasper, what do you think about all of this?
I mean, it's pretty amazing. We went from board games, and we talked about PageRank algorithms. What else did we talk about? We talked about these trains. We brought in things that are way away from our original Markov consumption. And now, I think that we can basically predict the future. So good luck out there with your Markov chains. Thanks for watching.